Hello, Chem 213 students, and welcome back for our second lecture this week about alpha carbon reactions. In the last lecture, we introduced the molecular intermediates, enols and enolates. Enols, a carry forward from the alcohol chapter way back from Chem 212, but also enolate ions formed when we treat carbonyls, aldehydes, and ketones with a base. We ultimately end up with the deprotonated enolate ions. Um, Now, these enolate ions can go on and react with the aldehydes and ketones that are already present in the reaction flask and produce other reactions. And also, there are other reactions associated with the formation of these products as well, and that's what we're going to get into today. So remember that when an aldehyde is treated with a hydroxide, an equilibrium forms where will have significant amounts of both an enolate and an aldehyde. So the hydroxide here is sufficiently basic to somewhat deprotonate these. They're the deprotonated forms of hydroxide, and then the deprotonated alpha carbon, the carbonyl, have pKa's that are similar to one another. Remember that. That's very important basic idea in this. And so if we want a reversible formation of an enolate ion, we can use a moderate base such as hydroxide. If we wanted to have an irreversible formation of that, we would use a stronger base such as LDA, or lithium diisopropylamine, which is analogous to our amide ion, but with some steric hindrance there to avoid some substitution reactions and so forth. But here we have a hydroxide ion. Ultimately, the product of the aldol reaction will be one in which we have an enolate ion that will be formed that will attack this carbonyl itself and add on carbon atoms. So this is going to be a new reaction where we can add on additional carbon atoms. When those atoms are added on, we'll maintain the carbonyl, but also have a hydroxyl group at the beta position, making this an interesting synthetically useful reaction. So the way in which this works is we start with the formation of the enolate ion. This is no different than what we had seen before. So we have a deprotonation, a reversible deprotonation of the alpha hydrogen here, the alpha proton, which leaves us with the enolate ion. Now the enolate ion can behave as a nucleophile, however, and so the enolate ion can perform a nucleophilic attack on the carbon electrophile here that's attached to the oxygen. And of course a carbon cannot have 5 bonds, so we draw this resonance arrow right here with the carbonyl. At that point, we're now going to have this group here is going to be an alkoxide ion, and so this oxygen here is now this one drawn right here. This is the alkoxide ion, and so notice there's another carbon here. That's this carbon. This hydrogen is this one that right here that remained, and then we have a connection here to this carbon. So there's a bond. This arrow represents the formation of this bond right here, and then we have the remaining ethanol. What was ethanol now is a larger molecule. Finally, this alkoxide ion needs to be protonated to produce the neutral final product, and so we have a proton transfer from water. And notice that this means that the base really catalyzed the reaction, right? Because it was consumed here, and then it will be reproduced at the end. And ultimately, the enolate here is the reactive intermediate, and it can behave as a nucleophile. And so this is a kind of behavior that we're going to continue to see throughout the rest of this chapter as we look at a variety of reactions that involve enolate ions as intermediates. The aldol addition is an equilibrium process, but for most aldehydes, the aldol product will be favored. Notice that we had equilibrium arrows in here. Not all the molecules at once would be deprotonated. We have a big mixture between enolate ions and the aldehyde itself here, or the carbonyl, and there's equilibrium across every step of this. You can also have we'll talk about the reverse of the aldol. We can have a retro aldol addition as well, in which the molecule will break apart. These are all in equilibrium, but the equilibrium does generally favor the aldol product for aldehydes. And so that's why aldehyde was showed as an example here. So for example, here we have the butanal, and again, if this is treated with the base here, we're going to get a deprotonation of one of these hydrogens here. So I'll draw those in. So yeah, there's two hydrogens, but it's only going to be one that's going to be involved. This is a negative formal charge. It doesn't look very good, but and this is the OH, and so the OH is going to start by deprotonating it and creating the enolate ion, and then once we have that enolate ion, that can perform a nucleophilic attack on the same, not the same molecule, but another instance of this butanal, and then we would end up with this product here. Notice that here the alcohol is this part. So all of what I'm going to cover in green here, all of this is this right here. Ultimately, with the water, the alkoxide that's formed here is protonated, and then the remainder is what connected right here. So you can notice it connected right here on the alpha carbon. We end up with a connection between the two groups, and then we have the remainder of this butanal molecule right here. That was what performed the nucleophilic attack. Now with ketones, the aldol product is not favored, and so this aldol condensation works best on aldehydes. The reverse process is just the exact opposite of the mechanism. It's referred to as the retro-aldol reaction. So recall in the last reaction, look at the last step here. The last step was a protonation of the alkoxide ion, right? And then that was preceded by the nucleophilic attack, and then the proton transfer, making the enolate ion, was the first step. So we're going to do the exact opposite here. We're going to deprotonate the alkoxide ion. We're going to end up with a loss of the aldehyde as a leaving group, and then we'll have a protonation of a carbanion there. And so that's exactly what we see here. So it starts off with a deprotonation of the alcohol group here, giving us the alkoxide ion. Then that's followed up by the loss of the leaving group, just the reverse of the nucleophilic attack that occurred in the aldol formation. Finally, that's going to produce for us one neutral carbonyl here, in this case a ketone, and also it's going to produce for us a carbanion with these two electrons here left behind on the carbon. So the final step is now the reprotonation of the carbanion, and we ultimately get back our hydroxide. Notice again, this is base catalyzed, and then the formation of a second molecule here of this acetone. Now, again, this is a equilibrium process here. The reaction can be pushed in either direction depending on what you add or what you remove. And also the hydroxyl again is a catalyst here. It is reproduced upon the end of the reaction. Now, if we form an aldol product heated under acidic or basic conditions, we're going to get the beta hydroxyl group here. However, and if it's heated, this can further go on to produce an elimination. So we've seen, way back in chapter 8 in Chem 212, we saw acid and base catalyzed eliminations, and so we can, again, if these are occurring in acid or base conditions, if the temperature is high enough, this will go forward to produce an even more stable product. And you can kind of see what drives this reaction, right? It's more kinetically, it's more driven by the entropy. So entropy is increasing here, and so we can see that increasing the temperature is going to increase the entropy term, resulting in more favorable right side here of the reaction. So this is really going to drive this reaction forward. And we'll, if we heat up, if it's too cool, then it will be kinetically driven and it won't go through this as quickly. However, if it's hot enough, the thermodynamics will become more important, and finally we will get the more thermodynamically favorable product, which is the alkene here, the elimination. So if we do this aldol condensation at elevated temperatures, we're not actually going to get the beta hydroxy ketone or beta hydroxy aldehyde in this case. We're going to instead get a carbon double bond at the between the alpha and the beta carbon here. So this is saying here, you know, if we do this at low temperatures, we're going to get the beta hydroxyaldehyde. But if we do it at higher temperatures, which really is just like room temperature, we'll get the alpha beta unsaturated aldehyde. So for the aldol addition here, again, just going back to this this same type of mechanism here, we have the deprotonation at the alpha carbon here. Again, this is an equilibrium process, since this enolate ion and the hydroxide ion have similar basicities. Their conjugate acids have similar pKa's, meaning the pKa of this is approximately equal to the pKa of water here, and so that's why we have this equilibrium again. And then again we have the enolate ion behaving as a nucleophile, undergoing a nucleophilic attack on the oxygen, and again same old mechanism here. And then we have the final protonation producing for us the beta hydroxy aldehyde. Finally, though, there's one more step, and that is the elimination of the water. So if this is occurring at higher temperatures, again, you're going to have an elimination of water, which will ultimately produce your alpha beta unsaturated hydroxy unsaturated compound here. It was not hydroxy, I mean alpha beta unsaturated aldehyde in this case. The here being the aldehyde and the unsaturation here being at the double bond. So the way in which this occurs is, again, the alpha proton is deprotonated here, and this once again produces for us a kind of enolate ion, but at that point we ultimately have, this is basically like a similar to an E1 reaction, but this goes through a negative intermediate instead of a positive one, and we then have the loss of the leaving group in the formation of the pi bond here. So under higher temperatures, you won't just get this aldol addition, you'll have a follow-up, the elimination of water, which will ultimately produce for us our alpha beta unsaturated aldehyde here. Now, in terms of the stereochemistry of this, very sensible in the stereochemistry. You don't have to think too hard about it. Just think about what would normally be the more thermodynamically stable product. It would be the one that would have, and kinetically it will be a big impact too. So when this is deciding, you know, the rotation under which this will be when finally the elimination occurs, it will be one in which we have the least steric hindrance, and so this will be generally a kind of trans orientation, or you know, opposite sides here for the more bulky groups rather than being on the same side here. So this is a little bit more steric hindrance. Here there are less. Now, because, you know, even when I say high temperatures too, really realistically, this is like room temperatures where you know, get the follow-up of the elimination after you have the aldol addition. So the result is that you're not even going to see the beta hydroxy ketone here. Instead, this is going to go straight through and do the elimination right here. So again, this elimination, base catalyzed in this case, is the removal of these as water and the formation of the double bond here, which we see right here. And so under, you know, normal reaction conditions here, you're going to just go straight to the unsaturated product here, the condensation product. Just a note about the word condensation. Whenever I think of condensation here, they're referring to this removal of water. So I think of like, water condensing on the side of my cold glass, the water, being removed from the air. I think about that when I think of the word condensation, which reminds me it's this removal of water here. Uh, the yields for the condensation are generally greater than that for the addition reaction. And it's really because the formation of this more thermodynamically stable product drives this reaction forward to completion. You have just basically a more spontaneous reaction due to the basically the favored entropy, because you end up producing the two molecules instead of the one. So these are not very entropically favored. That's why you can see they do better at low temperatures. We have 10 degrees Celsius here. These are going to be more entropically favored, producing for us two molecules from the two. And so these will occur, assuming we can overcome kinetic barriers at higher temperatures, we'll get a good yield of the condensation product. Now, one important question, hopefully, that you asked yourself is that if we're having these enolate ions attack carbonyls, what if we have any other kind of carbonyl there? Can it attack that one too? And the answer is yes. And this results in crossed Aldol reactions. Now, a lot of times, crossed Aldol reactions are not synthetically practical. And the reason why, you can see here, if we try to do a cross Aldol reaction here between this ethanal and this propanal, ethanal, eth, 2 carbons, aldehyde, ethanal, prop, 3 carbons, 1, 2, 3, aldehyde, propanal. Don't forget those naming conventions there. And so here we'll have the formation of an enolate ion, and either of these could form an enolate ion at any given time, because they both have alpha protons. Here the alpha protons are here on the ethanol. Here the alpha protons are here on the propanal. So if we get the formation of a enolate ion from the ethanol, that enolate ion can go and perform a nucleophilic attack on the ethanol, and then we would produce a product here where this part here is here this is the first ethanol, so the part in red here you can see, and then this is the second one, and this black line is the bond between them. Likewise, if it happens that our base deprotonates the propanal, we can get an enolate ion from the propanal, and again that would perform a nucleophilic attack on the other propanal, and we would end up with these 2 units of propanol, this one here being the beta hydroxyl group, now attached through this bond, and we have the other propanol group from the enolate ion here. And we can go further. We can have these cross Aldol reactions now. So we have, again, the nucleophilic attack here, and then we're going to have the formation of the alcohol when it gets protonated from the ethanol. This green line here ends up being represented by this black line, and then we have the enolate ion from the propanol here. And likewise, we can have an enolate ion formed from the ethanol undergo a nucleophilic attack, and we'll ultimately here get the beta hydroxyl group, and that we have the 3 carbons here from what was the propanol, and then we have the bond between the 2 groups here, and then we have the ethanol group attached here in the red. So we have a lot of possibilities, and again, so this makes this less synthetically useful unless we control for the alpha carbons on one of the aldehydes here. So for example, if we use methanol or formaldehyde, there will be no alpha hydrogens. Or if we have a benzyl group here, there will be no alpha protons. And so then we can really control which is going to be the enolate ion that attacks as a nucleophile and which is going to be the species that is attacked by the enolate ion. So again, yeah, crossed Aldol reactions are only practical if we know which enolate which is going to be the enolate and which is going to attack. Otherwise, we're going to get too many different types of products. So we can use formaldehyde along with some other aldehyde here, for example. And then it would go the same way. You know, we'd treat with the hydroxyl group. So we'd have the hydrogen here, we'd have the OH here, and we'd have a deprotonation. So this will grab the proton. Boom, gotcha. And will produce for us this guy right here. We'll have the enolate ion now, which I'll just draw in this fashion. Although your book often draws it in the other fashion with the negative charge on the oxygen, because that's like the negative charge spends most of its time on the oxygen due to its greater electronegativity. But at that point, we can have the nucleophilic attack right here, and then we'll have the formation of this alkoxide ion, which is ultimately protonated by water to produce our beta hydroxy aldehyde here. And so given that there are no alpha protons in the formaldehyde, we can do a cross-Aldol reaction with formaldehyde without any issues. The alternative, as I mentioned, is benzaldehyde. So benzaldehyde also has no alpha protons. And so likewise, we can form an enolate ion here, undergo a nucleophilic attack. Again, this will end up being a deprotonated alkoxide ion, which is protonated with water by the end, recovering our hydroxyl catalyst, our hydroxide ion catalyst rather. And then this whole group here now is attached with the bond that was formed by the nucleophilic attack, and we have the propanol part here as well. Of course, if we have any significant temperature, this is going to go on and undergo an elimination for us. So again, this hydrogen here will be removed along with this water, this hydroxyl. They'll leave as water, and we'll end up with the double bond here. So crossed aldol reactions are only really practical when we have only one of the aldehydes can produce an enolate ion. We want the other one to not have any alpha hydrogens. So that would include compounds like basically formaldehyde and benzaldehyde. Those are our options. Now, what we can do is for cross aldol reactions, we can minimize the number of products in a different way. We can use LDA as a base, which is referred to as doing a directed aldol addition. So one compound is going to be completely converted to the enolate ion with LDA. Then we can follow that up with a step where we do then the nucleophilic attack. Because remember, when we treat with the sodium hydroxide, we get this reversible formation of the enolate ion. But what we can do alternatively is in a kind of separate flask here, we can treat with the LDA and we can collect the enolate ion, and then we add to that enolate ion another aldehyde. Then we can be assured that we know which was the enolate ion that was formed. So in this case, we're reacting acetone here, or 2-propanone, as it would be regularly called by the IUPAC conventions. And that would be our enolate ion, and then that enolate ion will go ahead and do a nucleophilic attack on this propanol here, and that will produce for us, here we have the deprotonated alkoxide ion. We leave it as deprotonated because we're assuming that this still is occurring in very basic conditions. So we have it deprotonated here, but we have these 3 carbons, 1, 2, 3 right here. This bond that's forming between them by the green arrow is represented by this black line, and now we have the whole acetone group here is attached. So we can do it that way as well. So if we don't want to do it all in one pot, if we want to do it step by step, we can deprotonate the alpha hydrogen on a ketone or aldehyde here with LDA, and then expose it to the other carbonyl reactant. Also possible, if we have diketones or dicarbonyls here, is we can do an intramolecular aldol reaction. And so intramolecular aldol reactions will occur in the same way as the ones that are between 2 molecules. It's just all happening within 1 molecule. And so let's break this down step by step. We'll start with the hydroxide here. So here we have a symmetrical diketone here. And so it doesn't really matter which hydrogen we choose to remove. I'm going to now deprotonate this guy here. So with the hydroxyl group. And so now we end up with the compound here like this. I'll just draw it over here where I've got some room. We end up with this kind of an enolate ion here. Like that. And so now if we draw this in a little bit different way here, oops, I deprotonated the wrong spot, sorry. Oops, I deprotonated on the inside. Strike that. I deprotonated the wrong spot, so sorry about that. So we're deprotonating right here instead. This is also an alpha hydrogen, and although we could deprotonate in the middle, the issue is that it's going to be a little bit sterically hindered, and so I was kind of like let my brain go loose on that a little bit too quick there. There we go. This will be less steric hindered. So we're going to have instead a product that looks more like this. So it's got the negative formal charge here on the end. Okay. And essentially what's going to happen is this is going to be the nucleophile that attacks itself, right? And so what's been drawn here is this is drawn out more in a ring style. So you can see the attack a little better. So here's the carbon that was deprotonated. Then we have the carbonyl carbon right here. The next carbon, that's this one right here. The next one here is this one here. And finally, this is the carbonyl carbon here, and it's one more carbon. So then we can have a nucleophilic attack of this enolate ion on its own carbonyl right here. And of course, the carbon can't have 5 bonds. So we draw this resonance arrow. And then at that point, we're going to get a product that looks like this. So now our number of carbons in the ring is going to be 1, 2, 3, 4, 5. 5 carbons in the ring. Okay, so we'll draw a ring with 5 carbons. Now this carbonyl here, drawing the upwards position, that's this one here. Okay. And then this bond here, this is the one that formed. This is the new bond. So I'm just going to kind of highlight that. This is thick one here. This is our new bond right here. Okay, that was formed. And these are the other carbons. 1, 2, and then 3 for the carbonyl carbon. Okay. And then on the carbon that is at the end of this bond, we're going to have a deprotonated alkoxide ion here. And we have this other methyl group, which is this one right here. This is this one here. This is this methyl group right here. Okay. And so now this would be protonated by the water, and we would get this hydroxyl group here, and then we'll have just an elimination, right? So this will be protonated, so this will end up being when it's protonated, I won't draw the mechanism of protonation, but this will be OH. Then we'll have a hydrogen here, and these will be eliminated in a E2 style fashion, and those will leave as H2O, and then we'll get the double bond right in here, and that produces for us this product here. And so these aldol reactions can occur in this cyclic fashion. So so if you've got a diketone and you're doing a synthesis and you want to end up with something with a ring, this would be a really good way to go. So esters can also undergo these types of condensation reactions. They are given a special name when they occur with esters. They're called Claisen condensations. And so when we do a Claisen condensation, the strategy here is going to be to treat with an alkoxide base where the alkoxide base has the same group as the ester. So we can see here we're using the alkoxide base, the sodium ethoxide as the base, and we have the ethanoate group here. And so notice that these are the same. The acid here is ultimately to protonate at the end. So let's go ahead and take a look at the details of this. But the ultimate endpoint of the reaction is that we're going to have one of these esters attack the other, but it's going to behave in such a way as we've seen with other ester reactions, where we're going to have an ethanoate group that's going to leave as the leaving group. And so you're going to see that you're missing one there, and that's why we use sodium ethanoate as the base, so that the same group that we have here, we get it back at the end when that leaves, and we avoid alternative reactions that may occur by the ethoxide behaving as a nucleophile. So Claisen condensation is simply a nucleophilic acyl substitution, as we've seen before in the ketones and aldehydes chapter. So the nucleophile in this reaction is going to be the ester enolate, due to the deprotonation at the alpha carbon, and the electrophile will be the ester itself, and your ultimate product here is going to be a beta keto ester. So you're going to get a ketone here at the beta position relative to the remaining ester group. So how does this work? Like most of these, this starts with the formation, like most of the reactions we've been seeing before, this starts with the formation of the enolate ion. And so we're going to have this alkoxide group. Again, note the fact that this alkoxide group and this one here, or the alkoxy group, and this alkoxide ion are of the same identity. This is important here. And then we're going to have the deprotonation to produce for us an ester enolate ion. And so this is behaving, just like our aldol condensations, right? This is where it differs, though. After this step, we're going to have the nucleophilic attack of the ester enolate onto the carbonyl carbon, which produces for us now this molecule, where we can see that this bond here, so this bond here, this is the bond that was formed by the nucleophilic attack. Okay. This one here, I got the wrong side. Let me erase that. Okay. We're going to go with green again. Okay, so notice that we had this ester enolate attack here onto this carbonyl group, and we ended up with the alkoxide ion here. So there's a bond formed right here. This is the green arrow corresponds to this bond here. We have this alkoxide ion, which is then going to undergo the loss of the leaving group, the OR group, as we've seen before in chapter 19. And so we're going to have then the kicking out of this alkoxide ion as a leaving group, which works, right? Because remember, we were starting with the alkoxide ion, so we're simply recovering it now. It's like the alkoxide ion was catalyzing this, right? And these are all reversible, these steps. Finally, though, we get a second deprotonation here by the alkoxide ion. And this is going to be a essentially irreversible deprotonation. And the reason why is because now notice we have a beta proton between two of these carbonyl groups. So that really lowers down the pKa. Remember, it's about pKa 9 here, whereas the pKa of the alcohol, the pKa of this is going to be approximately 16. And so this is a much stronger acid. This is a much stronger acid relative to a standard alpha proton in a single carbonyl, and so we get this deprotonation at the end. And that's why we need the last step for the acid workup, is because at this point this proton is so acidic, we're going to need something that's a stronger acid to protonate it. And so our stronger acid is whatever strong acid that gives us the hydronium ion. And so then we're going to have a proton transfer here from the hydronium, finally protonating and giving us the neutral product. So we have the beta keto ester produced. So there are some limitations. As I said, the starting ester, well, I didn't say this part, but the starting ester has to have 2 alpha protons because the removal of the second proton by the alkoxide ion is what drives that equilibrium forward. So here, this last step is what drives this reaction to completion. And so there's got to be a second proton here to deprotonate to complete this reaction. So you got to have 2 alpha protons to make this work. Also, hydroxide can't be used as the base. We need to use the alkoxide ion that is analogous to the alkoxy group on the ester. So notice again, when we say OR here, this OR is going to be the same as this OR. And the reason why we can't do hydroxyl is just as you see here. If the hydroxyl group I will do a nucleophilic attack, we'll end up replacing the OR group with the OH group. Okay, and then we'll have the deprotonation of that, and we'll end up, as we've seen before, when the carboxylic acid reactions, we'll end up with this carboxylate ion instead. So we have to use, and again here, if we use a different alkoxy ion instead of this one, again, we can have a substitution here of the one alkoxy group with the other. In this case, the methoxy group here does a nucleophilic attack on the oxygen. Then we have the loss of the ethoxy group, and now we've got a completely different ester. And so we want to use the same group here. So we'd want to use instead an ethoxide ion, so that if this substitution is occurring, it doesn't affect the identity of the ester rather. Okay. We can also, as we did cross Aldol condensations, we can also do cross Claisen condensations, but they're only going to be useful if we meet one of the 2 following criteria. First, the ester has to have no alpha proton. So this is directly analogous to the cross Aldol reactions. We want to know exactly in the first step what is going to be our ions that are formed as intermediates, and so we don't want to have to worry about deprotonation of the wrong alpha proton, right? So there's no alpha protons, for example, on this phenyl ester here. Only this ester has alpha protons, and so those are going to be the ones that will be deprotonated, and ultimately our beta keto group will be the phenyl beta keto group, and we'll ultimately get this this condensation here where we have the unsaturated alpha beta bond here and the deprotonated alkoxide ion. You can also, that's the same thing here as before. The other way we can achieve a successful cross condensation is controlling which enolate ion we produce by first deprotonating it with a very strong base, such as lithium diethylamide, and then getting that enolate ion, and then the enolate ion will do the nucleophilic attack here, and then we'll get ultimately we'll get the kicking out of this group. Notice that this group ultimately gets kicked out; it's not there anymore, and we'll have the double bond here and the deprotonated enolate ion, which we could then subsequently protonate with a acid workup. Like intramolecular aldol condensations, we can also have intramolecular Claisen reactions, which are referred to as Dieckmann cyclizations. So again, the same limitations apply. When we use our base, we want our base to be the alkoxide ion that corresponds to the alkoxy group on the ether. And we'll need acid as a final workup step to protonate the deprotonated carbonyl or former carbonyl group here, right? Or rather, the carbanion that is produced in the end. So here we can see what's going to happen. Let's kind of go through the details of the steps. So first of all, our alpha protons are at carbon 5 and carbon 2. we can remove these. This will be equivalent whichever one we remove. So there's 2 here. I'll just say, okay, we have, let's say we have our OET minus our ethoxide ion, and that's going to start by deprotonating here this alpha carbon, and then this is going to give us a carbanion. So I'll have the OET here. I'll have the and here will be my carbanion, which will do the nucleophilic attack. And so when this attack occurs, just like before, the carbanion is going to perform a nucleophilic attack here on the carbonyl carbon. And so that's going to produce for us this guy right here, OET. All right. And, whoops. I have to close the ring. Close the ring. So, okay. And so this carbon attacked here. So let's count how many carbons are going to be in our ring. This is going to be one of them, 2, 3, 4, 5. So this is going to be a 5-membered ring. And so we'll draw that. There's 1. So I'm going to call this, let me number them so we can keep track here. I'm going to call this 1, 2, 3, 4, 5, 6, like that. And so this is going to be 1, and this will be 2, and so forth. And so we'll go 3, 4, 5. Okay, and then attached to the carbon 5, 1, 2, 3, 4, 5. Okay, and attached to carbon 5 is going to be this this other group here, this whole ester group, OET. Okay, and this oxygen has a negative formal charge, and then the last step of the reaction is just going to be kicking out that ethoxide group, ultimately giving us, I numbered it a little bit differently than they did. I numbered it the other way around, but you get the idea here. So just kind of, I should have numbered it the way I did on the slide here. I just renumbered it again. But here, again, here, this is the ethoxy group that's hanging off here. It's 1 carbon away from the carbonyl, which is right here. So maybe I should just renumber these again just to correspond with the other ones. So if I renumber it again, I would really have 6, 5, 4, 3, 2, 1. This would be 6, 5, 4, 3, 2, and 1. And so we can see here the 1 corresponds to the ester group here, and the 6 is the one with the ketone in the end. So what we've gone through here in this last lecture is we discussed the formation of enolate ions and their ultimate attack on carbonyls in another molecule in the solution or in the same molecule. And we discussed this in terms of ketones and aldehydes, which gave us the so-called Aldol condensations. And we discussed this in terms of esters, which gave us the so-called Claisen condensations. In our next lecture, we're going to talk about a variety of other synthetically useful reactions, starting with the alkylation, the addition of a alkyl group on the alpha position of a carbonyl. And I look forward to having you join me for that next one. Have a great day.